I think we need to set the stage a little bit and talk about structured concurrency
Mm-hmm.
and what that actually is and why I should care. So convince me.
Okay, convince you. So, so first of all, let me just start right from the top. Is that I would recommend for you and for all the listeners, and really just anybody doing programming, or is to go ahead and read the blog post that kind of started. At least it might not be the one that coined the term structured concurrency, but I would say it was the one that brought it to prominence. And it's, for me, I can count on one hand the number of blog posts that have kind of changed my life, and this is one of them. And I wish I knew his name, but it's the author of the Python library Trio, which is a structured concurrency library. And what he argues in that article, which is such a great mix of being academic yet very approachable. So it's very thorough, very well annotated, but it's a very accessible argument. He talks about what makes abstraction possible, and he talks about the original conception of structured programming, which we all appreciate structured programming now because it's like a fish. It's the water we swim in. It's like us, it's the air we breathe. We don't think about the guarantees that if statements provide, that while loops provide, that functions provide. But he encourages us to think about that being a revolutionary idea in the 60s and early 70s, where if you enter a curly block, you know that control will pass out towards the end of the curly block. So if you enter an if statement, by entering that curly, you will exit, control flow will exit through the curly. Same thing with a while statement, same thing with a switch statement, same thing with a function call. And what this does is it allows us to make abstractions, because when I call a function, for example, I know that the only place that I can return is to that function site. And so it means that I can build abstractions on this function, because before the existence of structured programming, if you were to call a subroutine, that subroutine could like jump to somewhere else in memory and start executing instructions, and you might never return. And so it's just you can kind of leak flow control. And so what the concept of structured programming is at its core is that you want to, or that is tying the lifetime of concurrent processes to a lexical scope. And what that means is literally what you see is what you get. So if I'm looking at a piece of my program and I'm looking at a single lexical scope, I know that everything that I create in there is going to be gone after I exit that lexical scope. And this is something that's applied not just to flow control, but it's very familiar to us in terms of memory. So we don't have to, this is not like when we're writing JavaScript or we're writing Java or we're writing Go or literally any kind of modern programming language. When you allocate a variable, you don't have to think it's, if you allocate a variable inside of a function, you don't have to deallocate it, because you know that once it passes out of scope, if you're using a garbage collection system, it's going to notice that it's not part of the root set anymore, and the garbage collector is going to reclaim it. If you're doing something like Rust, it's going to say, okay, this thing is there's no owner for this object. We're gonna destroy it. And so this is the same thing for concurrent processes. So every concurrent process in a structured concurrent system is going to be bound to a lexical scope. So when I exit that lexical scope, that thing is not going to be able to survive. And I won't be able to exit my lexical scope until all the processes are finished. And why that's important is it just means that you want two things. Kind of the superficial reason is that you can't leak resources because every resource has a very, very delimited lifetime. And then I would say the bigger thing is you can build abstractions around it, because every single operation is atomic.
I think it's worth like talking about the native JavaScript stuff or the places in native JavaScript where you're running this problem. So promises aren't actually that great of an async concept, and it'd be nice to talk about a little bit more about that. And then you were talking about cleaning up resources. So there's a new spec for the what is it?
The explicit resource.
Yeah, so we have like some new tools to sort of help do that. So if it's like you're allocating something, you want to deallocate it out of scope. But historically, we haven't had that, and it's been really easy for, you don't close the database connection when you thought you should have, and then something blows up later. So whichever path you would like to talk, if you want to talk about like cleaning up resources or maybe promises, because that's something general, I think either of those I think would be really good to dig into a little bit.
Okay. So but we can talk about cleaning up resources. So in affection, and I would say in structurally concurrent systems in general, you not just a task or a promise or some concurrently executing code, but literally everything that has state is associated with that lexical context. So it's like a variable that's allocated on the stack, and when the stack is popped, it you make sure that that resource will be cleaned up. And I will get into why the explicit resource management and async await are really not adequate and up to the task, which is why other language runtimes are not adopting them. You'll notice that is unique to JavaScript, and nobody else is doing that. So allocating a resource really is just like allocating a variable on the stack. But it's more than that too, because you have to be able to handle things like errors in a uniform way. So if I have a scope that raises an error, I need to make sure that that error is caught. This is actually a problem in async await. And if you go out there, you can see a lot of people, like if I do a promise.race and I'm racing 20 promises against each other, and one of them fails, what am I doing? What do I do with the other 19? And the answer is they'll just keep running. You've basically leaked those processes. So this is one thing you can look at when you see a promise.race. You're almost always looking at a memory leak. And the most insidious thing about it is this memory leak doesn't actually appear until you're at scale, because it's not leaked outright, in the sense that eventually, probably, maybe, these promises will resolve. Maybe they resolve after 10 seconds. Maybe they resolve after 10 milliseconds. But they're still kind of out there hanging in the ether. And if you're in development and you're only handling a very small request load, or your event stream is just a trickle, it's not going to be a problem. You're not going to see it. It's not going to have a large impact in your memory relative to the total impact of the system. You take that same code and you put it under really heavy load, and your event stream is more of a fire hose. Then all of a sudden, each event leaking a small amount is still going to really, really stack up. And so one of the things I think that we fight against most when we're trying to evangelize this approach is getting across the idea that you don't always see these problems until it is way too late to fix them, and you're in production and you're handling a big load and you're like, oh my god, I'm leaking all this stuff all over the place. It's the same thing happens with a promise.all, except in the error case. So if I'm awaiting 20 promises with a promise.all and one of them fails, then I'm going to throw the error immediately, and the other one, the other 19 are leaked. So the race, you get the positive case, one resolves, you leak the 19. All, one fails, you leak the 20. Although I guess race is both positive and negative. So that's one of the reasons that our primitives and async await really aren't adequate. So whereas affection, you're forced to handle every error. So if any of those operations, those concurrent operations, fails, it's going to percolate up the stack. The other reason, and this is a really, really big reason, is that there is no way to resume or reclaim control of an async function once it is awaiting a promise. And this is really the most fundamentally broken thing about async await, is that if I have an async function and I say await new promise and that promise never resolves, I have leaked that async function. So you have no control. So whenever you await, no matter how long that thing takes to run, maybe it could be 5 years that it takes that promise to resolve, the async function that is awaiting that promise cannot resolve. It cannot settle for 5 years. And that's an extreme case. But again, you have the same case where if you, sorry, that's extreme. But again, you have the same case, whereas if you're awaiting a lot of promises and they're taking a long time, there's just no way that you can back out. And so everything in that chain of causality is also leaked. So I could have a promise, I could have a call stack that's including a module from NPM, that's including a module from NPM, that's including a module from NPM, and inside there, it's got a promise that's not resolving, and that's going to cause everything up the call stack to leak. So one of the requirements of structured concurrency is that the lifetime of an asynchronous operation has to be controllable by the outermost scope, not by the innermost scope. And that's the problem with async await, is the lifetime of an async operation is determined by the lifetime of its innermost promise. Whereas in affection and other structurally concurrent systems, the outermost operation, the outermost async operation has control to say, nope, we're done here. I don't not need it anymore. And you just fold up everything from down on down. And so it doesn't matter what's going on at the innermost level.